Well, let's see, maybe I'm lucky. We're gonna go into t-test now. Yeah, no. All right, hold on a second. I have to cancel my Jupyter notebook. You guys know how to stop your Jupyter notebook? No. Okay, that's all right. You can go to quit, right? But I don't like doing that. You can actually go directly into your terminal that you started it, Control C, and then start it up again. So you'll see a new one come up here. I need to fix this. It's in my environment. I did something weird at some point, but I don't got time for that. All right, so let's restart that. It's one of these notebooks too that's messing me up. Okay, so let's try to do our t-tests. So first thing to talk about is when we talk about the z-test, which was introduced like way at some point in the curriculum. I don't like to talk about it because, for the record, you almost never use a z-test directly in statistics because you assume too many things. So one of the assumptions for a z-test, the distribution is normal. It's a normal distribution. But that's not necessarily true, right? So we can actually have modifications to this. So a t-distribution, usually called students' t-test, t-distribution, which is kind of a fun little story. Basically, the reason we call it students' t-distribution is because William Gossett, it's not called the Gossett distribution or something like that. Basically, he wasn't allowed to publish under his name. He actually worked for Guinness Breweries, which, yes, the same Guinness that makes beer. He actually worked for there. They basically was doing statistical tests, and he wasn't allowed to publish under his name. So he put students, a student was published, even though he wasn't really a student. So anyway, now it's called the students' t-test instead of the Gossett t-distribution or whatever. But the main thing about t-distribution is basically think of it as a modified version of the normal distribution. And this is where, degrees of freedom, right? So degrees of freedom, basically the more data we have, the closer we are to a normal curve. So you can see here, I have a couple graphs that I grabbed from another resources and YouTube wrote this, but you can see, I believe in blue here is the normal distribution, and you can see a t-distribution right here. And this is with 1 degree of freedom, okay? So the more degrees of freedom, as you see increase, basically more data you have, you can see that in red, it's kind of like the new one. And then there's some green ones underneath here. It gets closer and closer to this normal curve. So you see 1 degree of freedom, 2 degrees of freedom, 3. And notice that these tails right here go down. And so I want you to think like this conceptually. The reason why the t-distribution does this is that if you have less data, even though these things are relatively low, if you just pull, let's say, one value, right, and then make the distribution from there, if the distribution is normal, you're really likely to pull off these really extreme values. So the probability of getting these extreme values are actually higher because you only have to pull one value from it, right? And so you can see there's kind of like these kind of fatter tails right here. And then as we get more and more data, well, it's less and less likely for us to actually pull those more extreme values, which is why we get closer and closer to a normal distribution. And you can see here there's 30 degrees of freedom. In general, what we say is that if you have at least 30 points of data, then you're pretty close, your t-distribution is pretty close to a normal curve. So it's arbitrary, but usually within 30, if you pull at least 30 people, or 30 data points, you are most likely to be close to a normal distribution. So that's kind of like why that, and sometimes you see like n greater than or equal to 30, basically to get into that normal normality assumption. Okay. Cool. So if you remember anything, just know that the t-distribution is the normal distribution, but kind of weird. Okay. Cool. All right. So just kind of, I don't know if this actually comes from the curriculum or this was something I wrote together, but just kind of show you a little bit like how we make this t-distribution. We can actually use SciPy directly. So SciPy can actually create this stats, right? SciPy stats, stats.t, and then interval. So know that right here, I can actually call the confidence interval, right? So actually create this right here, confidence interval of 0.95. This is just degrees of freedom. So this normally would be like the number of participants you have. Your loc and scale, which is super confusing, I think, in SciPy, but basically know that loc is basically that sample mean. So I'm actually creating here a t-distribution, saying, oh, it's going to be a t-distribution with a degree of freedom 99. Loc meaning the sample mean should be 65, but a standard deviation of 18. So we can expect it kind of like coming out like that. And just to kind of show you a little bit what this looks like, then we can have like a 95% confidence interval. You can actually calculate this directly. I'm saying, oh, from 29 to 100. So that means that 95% of those values, right, sorry, going from 29 to 100, we have our 95% confidence interval, which again, remember, means that if we were to resample this again, 95 times out of 100, right, we would get, we would actually have the true sample mean in there. And the true sample mean, or sorry, the true mean is 65. So there's 95 out of 100 times. If I repeat this 100 times, you might see this actually be out of the 65 level, but that's relatively rare. Okay, cool. All right, and then just kind of quickly showing you, here's a normal distribution. And I think, let's see here. You can see here that I built this up basically saying, okay, let me just get 100 or 500 different points. And you can see it's roughly normal. And you can see with the actual t-distribution, with the confidence interval, we can say, well, okay, using this data right here, we can say, okay, from these number of samples, we have our degrees of freedom, which is number of samples minus 1. So we're taking the mean from this. And then saying, okay, from the samples not mean, our sample standard deviation, so this is all calculated from here. We say, okay, the confidence interval for 95% goes from 22 to 87. And we can see the original, like the real, what's it called, mean is actually 54. So that actually kind of falls through here. So this is kind of like how, like, you can imagine this part. You would not normally do this part. This is like you get data, you load it in, right? You've can plot it out like this, and then you calculate your confidence interval. That's how you can pull this out. So you don't have to do the whole sampling thing that we talked about before. Okay, and that's the connection between that confidence interval, like how you can calculate it, versus like you like were to like bootstrap. Sound pretty good? Okay, any questions? Anything that, I don't know, like hopefully it's all kind of coming together, but like, okay, this is why we're kind of learning these different parts. Yeah, go ahead.
I have a question. Will we be using these repeatedly as we move forward?
Like
we're learning this now. Will we be applying it more as we go forward? Or is it like, okay, we're going to see it this time, then we're going to move on to another topic? Or is this like a piece of the other things? Will it build on each other?
Like how does this connect with the whole overall thing of data science? Is that what I'm hearing, right?
Yes.
Yeah. So one thing I will say is that you probably would want to, depending who you're talking to, you probably would want to report a confidence interval, right? And saying like, okay, this is like what our confidence interval in here. And that's more for a technical person. This can also be helpful for you to see like, what's the values that could possibly go through here. So this code probably itself is probably pretty typical. Like you would pull this up frequently. Now, it's hypothesis testing, and like it's on its own. When we talk about A/B testing, that's kind of what hypothesis testing is really related to. But let's say we talk about machine learning, you know, deep learning, stuff like this, analysis and stuff like that. That's not directly related to this. However, there will be aspects of it that like connect it together, if that makes sense. So for example, one of the machine learning techniques that we're going to do later in this module is linear regression. And linear regression actually relies on the sense of like saying, well, is this value actually significant in contributing to the overall prediction? And the way it's reported, guess what number they use to report if it's important or not? It's the p-value.
P-value.
So
yeah.
Exactly, yeah. So the p-value is going to be like, okay, like if you understand what the p-value means, it's going to be a lot easier to understand why this is like relevant. This directly, I'll be frank, is that if you're doing hypothesis testing, A/B testing, it's going to feel very much like very similar to like, oh, I'm going to run a statistical test. I'm going to check this out. But if you're doing machine learning, right, or let's say like any predictive analysis like linear regression and then other machine learning methods that we're going to talk about, you're probably not going to touch too much on hypothesis testing directly. However, there are going to be parts in there which will include like type errors and stuff like this. So type 1 error, type 2 errors, which again relates back to statistical testing itself with alpha and then later beta / statistical power. But they're not directly like built on top of each other, if that makes sense.
Okay. Yeah, okay. That does.
Good question. Good question though. But I think it's useful to know like how these all like really is like, but Victor, do I need to know this? Like, I think that's important. Like, I don't think there's any, like, honestly, I don't think you guys should ever feel ashamed of being like, but do we really need to know this? Because then you can see. But I will say is that you can go really deep into the statistics stuff. Like I will tell you, you probably do not need to go as deep as this statistics PhD has to go through, because honestly, it works well enough. If it works well enough, you're like, we can do other things to check this out. We don't necessarily have to use pure statistics just to get these values and stuff like that. Hopefully that's kind of reassuring too. And I don't know, maybe there's some statisticians that you kind of bump into later on in life who would completely disagree with me, and that's perfectly fine. What I will say is that in practice, you don't need to know every part of statistics.
I do, like, I remember doing this in my undergrad, and then when I did oceanography research, we used MATLAB, a little bit of R, and I would run ANOVAs. I would do all of this, but I remember it just being like there were, go ahead.
Like, was it more straightforward? Oh, like do this, do this, do this. Yeah.
Yeah.
Exactly. I feel like statistics can feel very much like turnkey, where it's like, oh, you write this code, write this part, you do these functions, you turn the key, you press enter, and you have the results. And honestly, that's how most statistics feels. However, that's why I kind of make it kind of clear is that it's not so much about being able to run stuff, because you can write a function like today if you wanted to, that's going to perform most of the things you're going to do. And you just say, oh, put the data in, turn the key, press enter, and then it gives you results. The important part is saying, first of all, how do I interpret my results? What does this actually mean in relation to my stakeholders? Like, how should I tell people, talking to my stakeholders, like, is it significant? The other part is saying, even if I can interpret this and stuff, is it the right thing to do? Like, did I consider all the assumptions? What am I actually doing in here? Like, it's really easy to mess up something, if that makes sense. Like, to state like significant results when they really shouldn't be significant, or at least shouldn't be reported as significant. And as a data scientist, you typically are talking to people, as a data scientist, like the reason why they hire you usually, it's like, hey, we don't know any of this stuff. You tell us what to do. And if you're not careful, you might tell someone to do something where really they shouldn't do that. Or you tell the more technical part and you say, for example, it's statistically significant, which is technically true, but like, should they actually act on that? And when you say something is statistically significant, stakeholders tend to think, oh, that means we should do something, like, this is really important, we should do this, because the phrasing sounds very much like that. And that's where I'm kind of giving you guys more of the tools of like, where's this stuff come about, and like knowing where it can fail too. That makes sense?
It totally makes sense. Thank you.
Okay.
Yeah.
No problem. Yeah, I think that I kind of went for a little rant for that, but I think that's kind of helpful to like see like where does stuff come from. Cool. All right. Cool. So I'm gonna go right into t-tests. And I'm kind of like just going next. So t-tests, I'm not going to go too much into it. Just a quick thing is basically, it's just like the z-tests. Basically, we calculate something called the t-statistic. And with that t-statistic, we determine, should we reject the null hypothesis or do we fail to reject the null hypothesis? Like I said, try to go n greater than 30. We have some things that we say, okay, we are comparing sample means, but we don't know the population. So we're pooling it, like, for example, let's say men and women to make a difference, right? And then we have the full population. We don't know what the true population looks like. Or, we don't know what the actual like populations for men and women for these values. And we have to estimate saying, well, is it significant, by basically not looking at everyone. So let's see here. Some quick assumptions, independence. So in an ideal world, everything should be independent, like the subjects, the samples should be independent from each other. So if you pick a sample, it shouldn't have any dependence on if you pick the next sample. I will tell you is that this is probably the most commonly broken one, and it's probably okay, where technically you can break this independence assumption and it'll work perfectly fine. And you can kind of think this, I like to think of it in certain ways, that nothing is independent, everything is connected together at some level. It's just to what degree, and that's kind of like what these assumptions kind of do. And so what's the good thing is that students t-tests, and later we'll talk about Welch's t-tests, those things are very robust against independence assumption. So you can probably have something that's not quite independent and be perfectly fine. So in general, to be honest, people usually ignore this part because it's like, yeah, it'll probably work fine. Okay. Randomly sampled, again, that kind of falls a little bit with independence. And then population data is likely normally distributed. Again, these are like assumptions that we say, oh, nice to have, but we're like, it's probably close enough. And we kind of proceed forward. So in fact, you probably will never see people even talk about these things, because it's like, unless you're a statistician PhD where you like really care about it. But data scientists were a little pragmatic and be like, hey, if it works, it works. And if we find something that's not quite significant, we can always test it in other ways or make different predictions. Yeah. Cool. So steps, like I said before, null hypothesis, alternative hypothesis. Write them down. Okay. Determine your significance value. If you don't know, it's probably 105. Okay. So that's kind of like depends on the situation. And then say how many deviations from the mean do we care about? And this right here, I wrote down this equation. Now look at it, appreciate it, and then forget about it. It doesn't matter. You're going to calculate this automatically. You're never going to do this by hand because you're probably, even if you do it from code, you can mess up your code. Use a statistical package. That's what they're for. So you can have other people look at it. But basically the main thing is saying how many standard deviations we are from the mean, and we have this t-statistic. Note that standard deviations comes actually from the t-test. So it's going to be slightly different from just looking at standard deviations to the normal, normal distribution. And then you find your critical value. So you say, okay, I have my alpha. I know I have my sample mean, X bar, right? This mu right here, even though it's the population mean, that's the kind of like what you're testing against, like with the alternative hypothesis or the null hypothesis. So this mu here, for example, could be like, oh, for example, on the packaging, we say it's supposed to be 33 grams in this whole bag of flour, okay? And then you randomly sample from your supply and say, is it actually 33 grams or are we lying to people or whatever? That's what your mu would be here, is basically what you're testing against. S being your sample standard deviation. Okay. And then we say, okay, we find your critical value. So we have, say, all right, we have our alpha, and we basically say, okay, from our alpha, and this is where it gets kind of confusing because no one ever shows alpha. People talk about as the p-value. Okay, so this is kind of like, has anyone ever seen like this old school like table, like back in like school at some point? Yeah, I remember these tables. We don't have to do these tables, but it's great. We have a computer that can calculate this for us. Otherwise, you have to use calculus to figure out the area underneath the curve. But we have computers, so we can be dumber. We don't have to worry about it. Not that looking at tables is any smarter, I don't know. Anyway, the main thing here basically is that we have our p-value, or alpha value, I should say. We have our significance value. We know how many samples are our degrees of freedom, right? So we basically put this in there. We've taken our alpha significance value. So these are the different alpha significant values. And that will translate to our t-value. So depending on what we care about the most. Note that in this chart too, they even show you significance value. So this is actually, if you look closely, p-value is 0.25, but it's 50% for a confidence interval. That's actually, this is because it's a two-tailed test. So that's kind of what's going on here. But if it's a one-tailed test, you just have the difference of just divided by 2 on this card. So, okay. So anyway, you basically plug in formula, you get a t-statistic value. Cool. Then you basically compare, I'm sorry, not t-statistic, t-critical value. You then compare your t-critical value with your t-statistic. So t-statistic's already been calculated out. Critical t-value is not based on your data other than how many samples there are and what test you're doing. You have this value, you compare, hey, is one bigger than the other one? Hey, it is bigger. Okay, we reject the null hypothesis. Oh, it's not bigger. Okay, then we fail to reject the null hypothesis. That's essentially what we're doing. Okay. And there, you got your answer basically. It's really significant. 5 easy steps. It's statistical testing is not really difficult when you really look at it. So I'm gonna skip over these samples, but examples. Do you guys have any questions about kind of like this overall steps of like how we do these tests, at least logically speaking, like this flow? Sound pretty good? Thumbs up if you sound pretty good. Sideways, you're like, I think I'm not there yet. Thumbs down, you're like, I don't know what's going on. Okay, I see thumbs up, so cool. All right, that's good.